This is the video for section 1.2, the notion of a limit. And in this video, we are going to talk about what it means to take a limit and see a few examples. So here's the graph of a function, f of x, and it has a hole at the value when x equals 3. So that hole means that my function is not defined at that point. And the question I would like to answer, or even know if there is an answer to this question, is what is the function value approaching as x gets closer and closer to 3? So, in other words, what is happening to the y values of the graph as the x values get closer and closer to 3? Now, the first thing that you'll notice is that f of 3 does not exist, f of 3 dne. But that's not what I'm asking. I'm asking what happens to the y values, to the function values, as x gets closer and closer to, but perhaps not equal to 3. And what you'll see is that it looks like they're getting closer and closer to 1. And in fact, that is what is happening. And so mathematically, we would say that the limit as x goes to 3 of this function f of x is equal to 1. And we denote it as I have written here, limit as x goes to 3, so lim sub x arrow 3 of f of x equals 1. Now let's give a precise definition for that, or quasi-precise. So given a function f of x, a point x equals a, and a real number L, we say that the limit as x goes to a of f of x equals L, provided that we can make f of x as close to L as we want by taking x sufficiently close to a but not equal to a. So if I can make those y values, those function values, as close to some number L as I want to by taking x closer and closer to a but not equal to a, then we say the limit as x goes to a of f of x exists and is equal to L. A good way to understand mathematical definitions is to think about what it means for a definition not to hold. And so what we would say is that if we cannot make f of x close to a single value as we take x closer and closer to a, then the limit as x goes to a of f of x does not exist. And I'd like you to think a little bit about ways in which a function could fail to have a limit. So graphs of functions that fail to have limits. And that's something we'll talk about a bit later. So here's an example. I would like you to approximate the limit as x goes to 2 of the function x squared minus 1 over x plus 1. Now there's a couple of ways to go about this. Perhaps the most naive way to do this is just to use a table of values. Because what is a limit asking? It's asking for the function values as x gets closer and closer to 2. So that may say to you, okay, what I'm going to do is I'm going to pick some x values, like say x equals 1.9. That's pretty close to 2. And I'm going to plug that into the function f of x, get out 0.9, and that's a pretty good approximation of my function value. And then I'm going to do that again. I'm going to take a number even closer to 2, like 1.99, and find that my function value is 0.99. And I'm going to take a number even closer to 2, like 1.999, and what I'm going to see is that my function value is 0.99. And then I'm going to say, well, it's just not good enough to take numbers that are slightly smaller than 2. Let's see what happens if I take a number slightly bigger than 2, like 2.1. My function value becomes 1.1. If I take 2.01, my function value becomes 1.01. And if I take 2.001, my function value becomes 1.001. So what does it seem is happening to our function values? Well, it sure looks to me like they're getting closer and closer to 1. So it looks like the limit as x goes to 2 of the function x squared minus 1 over x plus 1 equals 1. This is not a proof, but it is evidence to suggest that that may indeed be the case. So something else we could do to get an idea of what our limit may be is to look at a graph. So let's take a look at the graph of the function x squared minus 1 over x plus 1, and we're only interested in what it looks like near the point x equals 2. So if I draw it, it looks something like this. Oh, and that point should be filled in. Sorry. So we have a straight line here, and you can think about why it might be a straight line. So we don't care actually that that point is filled in, because we don't care what happens to the graph when x equals 2. We just care what happens to the graph when x is near 2. And what does it look like the function values are approaching? Well, it looks like both of the function values as x gets close to 2 from above and close to 2 from below, it looks like our function values are approaching 1. So again, it seems that the limit as x goes to 2 of x squared minus 1 over x plus 1 is equal to 1. But again, that is not a proof. It's just evidence. The only way to prove that a limit is what you are suggesting it is to accurately use algebra. So let's think about what this means. As x goes to 2, the quantity x squared minus 1 is getting closer and closer to the quantity 2 squared minus 1, which is 4 minus 1, which is equal to 3. And in the denominator, as x goes to 2, x plus 1 is going to 2 plus 1, which is also equal to 3. So as x goes to 2, the quotient x squared minus 1 over x plus 1 is going to 3 over 3, which equals 1. And so that's an algebraic proof that the limit as x goes to 2 of x squared minus 1 over x plus 1 is equal to 1, just like we said it was. So we used algebra to show what we kind of already knew via numerical approximation and via a graph. So let's look at another example, a slightly more interesting example, and let's do the same 3 methods for getting evidence about the limit and then actually proving what the limit is. So same function, x squared minus 1 over x plus 1, but now I want you to take the limit as x goes to minus 1. So let's first approximate that limit and use a table of values. So let's let x be negative 0.9, and then f of x is negative 1.9. If x is negative 0.99, f of x is negative 1.99. If x is negative 0.999, f of x is negative 1.999. If x is slightly smaller than negative 1, like say negative 1.1, then f is negative 2.1. If x is negative 1.01, f is negative 2.01. And if x is negative 1.001, then f is negative 2.001. So from this table of values, it appears that the limit as x goes to negative 1 of f of x is equal to negative 2. That's our guess. That's what we have some evidence in support of. Next step, or next thing we could do, is let's graph x squared minus 1 over x plus 1 near x equals negative 1. And the first thing you should notice here is that this function is undefined when x equals negative 1. We get a divide by 0. So something is going to go funky on our graph. And what it's going to be, and for this you have to sort of use some knowledge about graphs, is we're going to have an open circle. A divide by 0 does not necessarily mean a horizontal or a vertical asymptote, and we're going to see that shortly. What we have here is we have an open circle at the point negative 1 comma negative 2. But we don't care what happens at x equals negative 1. We just care what happens nearby, and nearby x equals negative 1 is sure as heck looks like the function values are going to negative 2. So again, more evidence that the limit as x goes to negative 1 of f of x is equal to negative 2. Now let's see if we can use algebra to prove that precisely. And indeed we can. So the limit as x goes to negative 1 of x squared minus 1 over x plus 1 is the limit as x goes to negative 1. I'll factor that numerator into x plus 1 times x minus 1 divided by x plus 1. And we see we have a common factor, x plus 1 divided by x plus 1. So I'm just going to cancel willy-nilly, right? Wrong. I'm going to do a careful cancel. Remember, I can only cancel things if I make an argument as to why they are not equal to 0. And the reason x plus 1 is not 0, which is equivalent to say x is not equal to -1, is because we are taking the limit as x approaches -1, which means x never actually equals -1. So once I make my careful cancel, then I have the limit as x goes to -1 of x minus 1, which is -1 minus 1, which equals -2. So indeed, I have used algebra to prove that my limit as x goes to -1 of f of x is indeed -2. Your exercise for this guided practice is in figure 1.5. Please tell me what the limit as x goes to 0 of g of x is.